So we saw earlier with the basketball example that conditional probabilities are not equivalent when they're switched. The example that I used was that the probability of being tall, given that you are a basketball player, is much higher than the probability of being a basketball player, given that you're tall. And I don't believe I mentioned it in that video, but there's a name for this idea. It's something known as the Prosecutor's Fallacy. And I think I knew this in the back of my mind, but I recently came across some example that lays out exactly why this is the Prosecutor's Fallacy and not something like, I don't know, the cashier's fallacy or the accountant's fallacy. And it goes like this. It says, suppose that a partial smudged fingerprint is found on a weapon left at a crime scene. A fingerprint database search reveals that a person who lives in the same city has a fingerprint that matches the one left on a weapon. A forensic expert testifies that only 1 in 1,000 randomly selected people would provide such a match. The prosecutor argues that, based on the forensic expert's testimony, the probability that the defendant is innocent is only 1 in 1,000. Now, this seems pretty logical, right? Wrong. The prosecutor is confusing the probability of a fingerprint match given you are innocent with the probability of innocent given a fingerprint match. And let's see how this actually works. Let's suppose that we're in a city with a large population, say 1 million plus 1 residents. Given that the defendant lives in a city, the probability of them being innocent is this huge probability right here. Whereas the probability of them being guilty is this extremely tiny probability. These are our priors. And as we know, the forensic expert testifies that there is a 1 in 1,000 chance that some randomly selected individual from the city will match the fingerprint left on the weapon. Therefore, we can deduce that our likelihoods are the following. The probability of a fingerprint match given innocent is 1 in 1,000, whereas the probability of a fingerprint match given guilty is 1. From these, we can calculate that our proto-posteriors, and this is actually a new term that I haven't used before, but all it means is the calculation in the numerator of Bayes' rule. It's just so much easier to say than like probability of A times probability of B, blah, 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 blah. But anyway, we can see that our proto-posterior for the first situation is this huge probability times 1 over 1,000, giving us 1,000 divided by 1,000,001. The second proto-posterior is 1 divided by 1,000,001 times 1, which gives us 1 divided by 1,000,001. Now, we can calculate the posteriors of each probability by dividing our proto-posteriors by the normalization constant. And if you don't remember the normalization constant, it's super easy. All we do is take the sum of the two proto-posteriors. So we can see that the proto-posterior for situation 1 divided by the normalization constant gives us a probability of being innocent given a fingerprint match of 1,000 divided by 1,001. Whereas the probability of being guilty given a fingerprint match is only 1 out of 1,001. It's almost guaranteed that the person who got dragged into this mess is innocent. And now this is very intuitive. Out of the 1,000,001 residents of the city, there is only one person who is guilty of this exact crime. Hence, the probability of guilty given a fingerprint match is 1 out of 1,001. And that's it. That's as simple as it can be. Hopefully next time you're falsely accused of some violent crime, you can use this to your advantage. And if you do, maybe you can email me or something, because I would love to hear about that. But anyway, I actually want to do one more example that focuses on a different topic. A common misunderstanding of students who are just starting to learn about Bayesian models of perception is that unequal priors are, for some reason, some sort of necessity. And I've touched on an example that disputes this in a very non-mathematical way, this birds on a wire example, but I wanted to dive a little bit deeper into it. Suppose that you observe 5 dots which are all moving downward. Most people would perceive these dots as being a single group or a single object. And just an interesting side note, this actually comes from something known as common fate in Gestalt psychology, which is defined to say elements that move in a synchronized or coordinated manner are perceived as belonging to the same group. But Bayesian models can help us gain a little bit deeper of an understanding than just this definition on a screen. Let's denote each dot as a sensory observation: I1, I2, I3, I4, and I5. The first step in Bayesian modeling is to develop what's known as our generative model, a graphical or mathematical description of the possibilities that could have produced our observation. And to simplify some things for ourselves, we can assume that we only considered two possibilities. Either one, the dots are all part of a group and always move together, up or down, with a probability of 1/2, or that the dots are all individual and they move independently to each other, either up or down, also with a probability of 1/2. Now, let's consider the specific observation that we encountered, which was all 5 dots moving downward. The challenge that we have just given our brain is to deduce whether the dots were part of a group or individual. And we already have our priors, so let's go ahead and find our likelihoods. The likelihood of all the dots moving down, given that they are part of a group, is just 1/2 because the group can either move up or down. But the likelihood of all the dots moving down, given that they are individual, is much lower. It's 1/2 times 1/2 times 1/2 times 1/2 times 1/2. It's 1 out of 32. So it would be quite a coincidence if we were to see all the dots moving in the same direction, given that they were individual. And now, having our likelihoods, we can go through the motions again. Calculating our proto-posteriors, we see that the proto-posterior of the dots being part of a group is 1/2 times 1/2, or 1/4. And we can see that the proto-posterior of the dots being individual is 1/2 times 1/2 raised to the 5th power, or 1/64. And now we can find our normalizing constant. And finally, we can divide the proto-posteriors by the normalizing constant. So we can see that the probability of the dots being part of a group, given that they all move downwards, is 16 out of 17. And we can see that the probability of the dots all being individual, given they all move downwards, is 1 out of 17. So there we see it. That's concrete evidence of the Gestalt principle of common fate, which that's pretty cool, but most importantly, it serves to dispel the notion that unequal priors are for some reason a necessity for good prediction using Bayesian inference. With this example, we started with an equal prior, each probability 1/2, and still ended with very unequal posterior predictions. So, I hope all of this made sense to you. If you have any questions, as always, feel free to leave them in the comments. I'm happy to answer them. But yeah, thanks for watching. Don't forget to subscribe, and I'll see you next time.